Chapter 9 talks about polar coordinates. Your entire life, you have been graphing functions and points and coordinates on the x-axis and the y-axis, right? Now, that's not the only set of axes out there in the universe, all right? The polar coordinate system has nothing to do with polar bears or whatever else. It's a two-dimensional coordinate system in which each point is determined by a distance from a fixed point and an angle from a fixed direction. So, until now, we were using the x and y axes, as you see on the left there. These are called the rectangular coordinate system. It's also called the Cartesian coordinate system, named after our very, very lovely René Descartes, right? He also gave us the Cartesian coordinate system, as well as Descartes' rule. And so over there, in order to find a point, or in order to define a point, if you want to tell somebody that you are located at this point, you give them how much to go up or down and how much to go right or left. So you tell them, go 5 units to the right and 7 units up, and you will find me right there. And that's fine. It works for us a lot of the time. However, you can see how it might have some limitations, because guess what? Is the earth flat? Some people think it's flat, but you know what? It's not. What? It's round, right? And so the rectangular coordinate system, you can't, like, you see how, like, it doesn't really work. That's where we use a globe versus, you know, a rectangular map. And so in order to map things out, you know, in the universe, right, where things like can like expand radially, you know, things can move out radially like this, we use the polar coordinate system. Okay? The polar coordinate system is defined as follows. I don't like that. Okay. The origin, all right, just we have an origin in the rectangular system. Here the origin is called a pole, and the origin is that point right there. That's the origin, or the pole. We don't call it the origin, we call it the pole. All right. The polar axis is a ray that extends from the pole. This is the polar axis. It's horizontal, right? So that's the polar axis right here. Okay. Now, how do we define coordinates? Not as x and y. It's still two-dimensional, so we have two variables. Polar coordinates are defined as r and theta. So in order to describe a point, describe a location, you need to say how big r is. R is the directed distance from the pole, okay? So I am, you know, 3 centimeters out, I'm 10 centimeters out, and so on. And then you need a theta. This is the directed angle from the polar axis. So if I wanted to tell a person how to get to this point P, I could, just like before, I could tell them to go, you know, right 3 units, up 5 units. Or I could say, go out 3 units, and then rotate by an angle of 40, and I will get to the same point. You see that? So there are 2 different ways of describing the same point. And you see how when you're out in open space, how much easier that is to you know, describe a position. So now, how do we graph a point in polar coordinates? And you will all be given, you know, correct graphs for this axes. Now, a positive value of theta implies counterclockwise rotation. We know this because we've done chapter 4, right? Now, R, if R is positive, it lies on the terminal side of theta. So if you rotate 30 degrees, right? And you have like a positive value of R, your point is on that terminal side. But if R is negative, then you have to go on the opposite ray of the terminal side. So if R is negative, it lies on the opposite ray. Okay, so do you remember from geometry what opposite rays were? Opposite rays, so if you have this ray, and then that ray, right, it will form a line, right, but basically it's in the same direction, it's got the same angle, but in the opposite direction. Those are opposite rays. So take a look at this for a minute. Suppose you have a 30 degree, so this is the polar axis. All right. So suppose your theta is 30 degrees. You have a 30-degree rotation. And your R is 3 meters. You're right there. Okay? Now, suppose that's the polar axis. You have a 30-degree rotation, but your R is negative 3 meters. Now, instead of it being here, it's on the opposite ray, 3 meters. Right? So your P is now here, whereas P was up there before. Do you see what I mean? Okay. Just as rectangular coordinates are graphed on a rectangular grid, polar coordinates are graphed on a circular or a polar grid, which looks like this. All right, and I will give you a version of them to use. Okay, so the way this works is, you see how you have from the polar axis, right? The origin is at the center here. From the polar axis, you have the same old angles, right? Going in a counterclockwise direction. And then if you go radially out, each of these divisions is 1 unit, okay? So you could go 1, 2, 3, 4, or you could go 2, 4, 6, 8, whatever. You can still calibrate it as you like. So we are going to graph each point here on the polar grid. So first I have 4 pi over 3. I like to, okay, so just like it's always x comma y, and if it's, so if you have 3 comma 5, you can't write that as 5 comma 3, right? That's like a whole different location. Same thing here, it's r comma theta. You can't write it any other way. Okay, you can't reverse them. However, when I'm graphing, I do like to do the theta first, right? So if I were to graph 3 comma 5, doesn't matter if I go up 5 first or over 3 first, doesn't matter. I like to do the angle first. So go on 4 pi over 3, right? That's the that's this line here. Okay. My radius, so this is r, this is theta. My radius is 3. That means on that terminal side, I'm going to go out 3 units. So if that's the center, 1, 2, 3, there is my P. Okay?
Wait, how did you go?
The whole origin is here. I just go 1, 2, 3. What do these remind you of? Think of like, where do you see them in movies? Sonar, the radars, right? Radars. That's what this is. Okay. So here I have an R and a theta. Now I have negative 240 degrees. So I'm going to go I'm going to go in the negative direction now, right? Clockwise. where is, it makes a, okay, so negative 240
120.
is at the 120. But now, because this is negative 2, it's going to be on the opposite side. So 1, 2 here. Okay? Right? So I go negative 240. I was there. But now it's negative 2. So instead of the ray pointing outward, I mean this way, it's got to go here. So it's negative.
So it doesn't matter. So if the R is positive but the theta is negative, you don't have to do the opposite ray.
You do. So let's say it was 150 and negative 2, it would still be down here.
I know, but I'm saying, what if R is positive and theta is negative? Like it's.
Oh, yeah. Correct. Okay. Now, you can have multiple representations of polar coordinates. So let's do the first one, 2, 70. So again, I like to do 70 first. So 70 is somewhere past the 60, right? And then I'm going to go 2 units out. So do you guys agree with me that that would be where P is?
Yeah.
Okay. Next, I have 2, 430. Oh my gosh, 430. So I'm going to go around one time to 360. And then how much more am I going to go to make it 430? 70. Right? And 2. So look. Oh my God, it's the same thing. Well, because what changed from 70 to 430? I did theta plus what? Okay, so just like we know, if you add 360 to an angle, it's, nothing has changed. Okay, next I'm going to do negative 290. So negative 270 gets me here to the 90, and then I have to go 20 more. And then it's 2 units. Oh my God, it's the same place. Guys, look, it's the same place. Because what did I do here from the original theta? I did what? Minus what?
360.
Minus 360. Oh my God, so if you add 360 and subtract 360, nothing changes. You get to the same point, right? So we're just illustrating here what we already know, okay? Now, let's do another one. These are a little bit more exciting. We're going to do 53, 50 degrees. So 50 degrees is underneath the 60. And then now we're going to go 3 units out. So we're right there. That's P. Now, I'm going to go to 230. 230, so this is 180. 210. 230 is right before the 240. Right? But it's negative 30, so I have to go in the opposite direction. So instead of me being here, right, I have to go in the opposite direction. So I'm right there. Okay? If you like, you can draw a little guide, like a line to guide you. Okay. Next. Okay, so what did we do here? What did we do here? How did the coordinates change from the original? First of all, the R changed, right? Because now I have what? Negative R. And what about the theta? How did the theta change from 50 to 30 to 230? What did I do? Added 180. So look at what that tells you. If you change R to negative R, but add 180, you get the same coordinate, right? Because if I change R to negative R, and then I go around 180, I'm back at the same point. So what about this one? What does that one do? We're going to go to negative 130 degrees. All right, negative 90, 50 more, we're right here. But R is negative, so I go back out to the same point. Okay, what have I done now? I've changed R to negative R, and I've subtracted 180. Okay, so let's summarize this for a minute. How do I get coordinates of the same position? Different coordinates of the same position. I can do theta and add or subtract 360. Or I could do theta and add or subtract 2 pi. And I get the same position. Or I could do negative r and add or subtract 180 or pi. Okay? And here I've got some, the same thing, that it would yield the same angle. Okay, so let's practice here. You're given a point. You want your theta to be between negative and positive 360. You have to come up with 4 different coordinates to represent that point S. All right, so the first thing, just read that coordinate, right? Where is that? What's the radius there? I think it's 2. And what's the angle? 210. Okay. So next, what I can do is I can change it to negative r. And, okay, can I add 180? If I add 180, what do I get? But that's bigger than 360, so I can't do that. But I can subtract 180. And I get negative 2, 30. Next, I can keep it as r. Remember, so we could do plus or minus 180 or plus or minus 360. But I can subtract 360. And then I get 2, negative 150. Another thing I could do is I can take this coordinate point and I could do negative 2 and I can subtract 360 from here. So lots of different options. Okay? All right. Now, any questions so far? So just a heads up, what I'm doing today is only half of section 1. We are only going to cover sections 1, 2, and 3. I'm going to do half of section 1 today. Then I'm going to do section 2, and then I'm going to do the other half of 1 along with section 3. And the reason is it just fits better. And, I've researched, all over the place, and a lot of books do it that way, and I think it makes more sense to do it that way. So that's how I'm doing it. So this is only the first half of section 1, all right? And then I'll tell you about, the rest of the schedule in a minute. Okay, so we learned how to plot points, okay? Now let's graph some equations. An equation expressed in terms of polar coordinates is called a polar equation. What you've been graphing until now, the parabolas, the cubic functions, the trig functions, those are all rectangular equations. These are polar equations, all right? I don't need to tell you, right? Like how much I love polar functions and polar equations. Oh my gosh. Like so much fun. Think about it. How often is everything just like, go, vertical and horizontal? How often is it always that? Never. Like everything in the universe, it's always like, radially out. Like if you turn on a light, right? How does the light travel? Does it just go like horizontally or vertically, or does it travel like radially out? It travels radially out. If you send a signal, if you talk, how does your sound travel? It's like in circles radially around you. So this is a lot more practical for real life applications than those coordinate systems, the rectangular coordinate systems. Okay. So look at this one. So suppose you have an equation like this, r equals 2 sine theta, right? What is the polar graph of that one going to look like? Well, when you first learned how to graph back in like pre-algebra, y equals 3x plus 2, what did you first do? You picked points, right? Well, what if we do that here? What if we pick some points for theta, right? Can we do that here? If theta is 0, what's r? 0. If theta is pi over 2, what's r? What's sine of pi over 2? 1 times 2 is 2. So if theta is pi, what's r? 0, right? So you need to refresh in your mind all of that stuff, the unit circle, okay? So that's that. Now we need to graph these two. I want to graph each polar equation. So why don't we just pick points? All right, let's plot a point here. It says r is 2.5, right? R is 2.5. Okay, so from the origin, I'm going to go 2.5 at 1, 2, blah. Is there another location where I could graph that? Like I could put a point for r equals 2.5? What about when, at pi over 2? 1, 2, 2.5. Where else can I find r equals 2.5? Oh, right there. What about that one? Yup. What about this one? What about this one? And if you plot every single point that satisfies the requirement that it has to be 2.5 away from the origin, what shape are you going to get? A circle. So if you have r equals a number, that's the set of all points which are 2.5 units away from the pole, right? So this is the set of all points . 2.5 units away from the pole. In fact, the circle, the equation of a circle, x squared plus y squared equals r squared, it's just a derivation of this. Somebody took this and changed it to rectangular coordinates. It really came from this, okay? All right, what about that one? Now I want the set of all points, which are 5 pi over 6 away from that polar axis. 5 pi, is it array or is it a, well, let's see, 5 pi over 6 is, units, is one point is there. This one is also 5 pi over 6 units away. This one is also 5 pi over 6 units away. Where else? It's a line, okay? So if you continue, this one, right? Like these are, okay, and so you could go in the positive direction or in the negative direction, and that entire set of points, okay? That's a little too big. You don't have to make it that big. Okay, that's how you graph theta equals so-and-so, okay? All right, so that is all for this section. This is the homework. I have hard copies for those of you that are here today of polar graphs. They're blank, so you have to go and you have to put in, the angles, whether it's in radian or in degrees. You have to calibrate them. You can't just leave it blank. You have to write 30, 45, 60, whatever, or in radian. If you need more, I've put a file on my JAG right underneath where I have the notes that says blank polar graphs. When you open up that file, there are 3 or 4 pages. I normally just use page 1. Okay, so you can print more for yourself. All right.